Hello viewers, Wagadaruna taking you through the story for O-level physics. And this video I'm going to go through the topic of electrical energy and power. So this video is suitable for students in both Senior 3 and Senior 4. So this topic of current electricity has 5 parts of the calculations. We have already looked at the first part, second part, third part. Now we are on the fourth part, which is electrical energy and power. So you're interested in the calculation bit of it, but complete notes are available in the book called Mastering O-Level Physics, Volume 2 of 2. But we also have a topical question bank of O-Level Physics with marking guides, and a topical question bank of O-Level Math with answers. And if you need a copy of these, any of these, contact the author on these contacts. So you start our topic of electrical energy and power in electrical circuits. We shall start with electrical energy. So you have electrical energy and you also have power, electrical power. Let's start with electrical energy. So we shall come and say that when a charge moves through a resistance wire, the work done becomes the electrical energy, which changes to heat energy. And in that case, work done is equal to voltage times the charge. W denotes work done, V denotes the voltage or the PD, and Q denotes the charge. We already know that Q is equal to IT, where I is current and T is the time. Therefore, when I substitute for Q, I'll come up with W equal to V times IT. Therefore, this is one of the expressions of electrical energy, that work or work done, VIT. But also you know that V is equal to IR. Therefore, when I come and substitute for V here, I'll come up with IR times IT. Therefore, I'll get another expression which is I squared RT as an expression for electrical energy or work done. Then similarly, if I want to eliminate I remember that from here, when I make I the subject, it will be V over R. Therefore, come and substitute for I here. It is squared, so that's why I put it square here. And I will end up with V squared T over R. So that gives the third expression. So those are the 3 expressions for electrical energy in electrical circuits. The first one is IVT, another one is I squared RT, another one is V squared T over R. So in summary, electrical work done can be calculated using any of the following formula. So you can either use this first one or second one or third one depending on what is known. And the SI unit for electrical work done or electrical energy is a joule and is abbreviated by capital J. So when you're writing in full, it is a single J, begins with a single J, but when you're writing it as one unit letter, it is capital J. So that was electrical energy. Now we shall go to electrical power. Then from there we shall look at the calculations which are interested in. So power is the rate of doing work, or you can say power is the rate of energy transfer. So the word rate means time is included. Therefore, power is equal to work done over time taken if you're using this definition. Then if you're using this definition, then power is equal to energy transferred over time taken. Therefore, using symbols, work done is W, time taken is T. And we know that work done has 3 expressions. There is this, that, and that. Therefore, what I'll do, for all of them, I'll keep on dividing by time to get the expressions for power. So when I divide this expression by T, I'll come up with IV divide this by T, I'll come up with I squared R. Divide this by T, I'll come up with IV squared over R. So those are the three expressions for electrical power. So we have looked at three expressions for electrical work done and three expressions for electrical power. And power is measured in watts, or capital W if you're using a symbol. And a watt is defined as the rate of working of 1 joule per second. So with those formulae, we can go through these questions. Question 1 came from UNEB 2015 paper 2, question 6D. It says, given the circuit in figure 3, find Roman 1 the readings of the ammeter A1 and A2. Then Roman 2 the total power dissipated in the resistors. So this current, when it flows up to here, this junction, it divides. One goes this side, another one goes this side, until it divides, it joins here to go back to the source. So the first thing to do is to get the total resistance. These were resistors in parallel, therefore the formula will be product over sum to give you 4 over 3 as the total resistance. Now that I've got the total resistance and I know the total PD, I can get the total current, and total current will be 4.5 ampere. And now that I have the total current, I remember that the resistors in parallel have the same PD, so there is PD and there is resistance, meaning I can get the currents. Therefore, let I1, I'll come as that, let I1 and I2 be the readings of the ammeters A1 and A2 respectively. So for ammeter A1, if you look at this diagram, ammeter A1, the PD here is the same 6 volt, and the current, the resistance is 2 ohm. That is why here I'm using the resistance as 2 ohm and the PD as 6 to give you 3 ampere. What about ammeter A2? For ammeter A2, the PD is 6 volt and the resistance is 4 ohm. Therefore, I'll come and say that 6 over 4 to give you 1.5. So those are the readings of the ammeters A1 and A2. And for Roman 2, they asked for total power dissipated in the resistors. So total power dissipated is I squared R, where R is the total resistance, which I've already calculated as 4 over 3, and the total current we have already calculated as 4.5. So now you use the calculator, I'll come up with 27 watt, and that's what they wanted. Then question 2 came from UNEB 2013 paper 2, question 7C, and it says a battery of E.M.F 3 volt and negligible internal resistance is connected across 3 resistors, this and that, as shown in figure 7. Calculate Roman 1 the current supplied by the battery, and Roman 2 the power dissipated in the 5 ohm resistor. So first of all, these two are in parallel, and when they are combined they will be in series with this. So I already looked at arrangement of resistors, so you can go through the previous videos to internalize that. But for now, the assumption is that you know how to get the resistors in series and in parallel. So for Roman 1, first get the total resistance. These are the two resistors in series, in parallel, and when you combine them, they'll be in series with this one. And when I add everything, I'll come up with 6 ohm, which is the total resistance. Then the current supplied is total voltage over total resistance, which is 3 over 6 to give you 0.5 ampere. So that was Roman 1. Then Roman 2, the one the power dissipated in the 5 ohm resistor. So 5 ohm resistor, the current going through it is the total current. Therefore, you come and say that P is equal to I squared R. The current we use the total current, and the resistance is the resistance which was given in the question, and it gives you 1.25 watts. Then question 3 came from UNEB 2012 paper 2 question 7b, and it says a battery of E.M.F. this is connected to resistors, these ones, as shown. So still these are in parallel. When they combine, they're in series with this. Calculate the ammeter and voltmeter readings. That is Roman 1. Roman 2, find the rate. When they say rate, it means power. Rate at which electrical energy is converted to heat energy in the 6 ohm resistor. So they want the power dissipated in the 6 ohm resistor. So here for the whole circuit, total resistance will be given by first combining these ones in parallel, then add on to this one in series to give you 5 ohm. Then the ammeter reading, total PD over total resistance to give you 2 ampere. Now for parallel combination, voltmeter reading will be I times R parallel. So R parallel is the resistance for the parallel combination, which is 2.4. And the current is 2 ampere to give you 4.8 volt. So that is the voltmeter reading. Then for Roman 2, the one the rate at which electrical energy is converted to heat energy in the 6 ohm resistor. Now the good thing, we know the PD because the voltmeter reading is the PD across this parallel combination, and we know the resistance. Therefore, so for the 6 ohm resistor, we shall say that power dissipated is V squared over R. So V squared is the same as PD across the parallel combination, which is 4.8 is squared, and the resistance is this resistance of interest, which is 6. So we'll come up with 3.84 watts. Then question 4 came from UNEB 1998, paper 2, question 8b, and it says a battery of E.M.F. 10 volt and negligible internal resistance is connected to resistors, these ones, respectively as shown. This is the diagram. Part A, calculate the effective resistance of the circuit, and part B, find the rate. When they say rate, it means it's power. Rate at which electrical energy is converted to heat in R3. So they want power dissipated in R3. So first to get the total resistance. So total resistance, we first combine these ones in parallel, then they'll be in series with this one to give you 5 ohm. So it's somewhat similar to the one you have just done. Only that in this one now the power they want is no longer the one in the parallel combination. So here they want the power across power dissipated in the in R3. So when you know the total resistance, you can get the total current, then you say I squared R. So current supplied is V total over R total to come up with 2 ampere. Therefore, power dissipated will be I squared R3 to give you I here and R here to give you the 10.4 watts which they wanted. Then question 5 came from UNEB 1994, paper 2, question 5D, and it says an accumulator of E.M.F. 24 volt and internal resistance 2 ohm is connected to these resistors as shown in the diagram. Calculate Roman 1, the current through the 6 ohm resistor, and Roman 2, the total power expended. So first of all, these ones are in series. Then when they're in series, they'll be in parallel with this, and at the end they'll be in series with this. So the ones in series are these ones, When you combine them, they'll be in parallel with this 6 ohm resistor, and when you combine these three, they'll be in series with this 3 ohm resistor. But to understand this kind of arrangement, it's better you first look at the video of arrangement of resistors both in series and in parallel, so you can easily understand what you are doing now. So in the end, you shall come up with 6 ohm as the total resistance. Then EMF is I in brackets R plus R. So R is external resistance, internal resistance. So come and substitute for EMF, external resistance, and which is the total resistance, and the internal resistance, which is 2. So we have only I, which is the only unknown, so make it the subject to get the current in the circuit, total current in the circuit. Then PD across the parallel combination is IR parallel. So R parallel will be this, is the whole of this, which is this 3 ohm. That's why you see here 3 ohm. And this current is 3 because here we got 3 or so. So we multiply the 2 to come up with 9 volt. The current through the 6 ohm resistor will be V parallel over R4, where R4 is this ohm, and V parallel is this 9, to come up with 1.5 ampere. So that was Roman 1. Then Roman 2. Roman 2, the one, the total power expended. So we know total current and we also know total resistance. So total power will be, that is one way, but here total power expended to be EI. Now power expended and power dissipated, they are not the same. So power expended is like power generated, so that is EMF times current, or IV. So EMF was 24, current was 3, to give you 72 watts. Then question 6 came from UNEB 1993, paper 2, question 6D, and it says, when two identical heating elements of a kettle are connected in series to a 240 volt supply, the power developed is 400 watts. Find Roman 1, the resistance of the either element. Remember, they are two and they are identical. Then Roman 2, the power developed when the elements are connected in parallel to the same supply. So let R be the resistance of either element. Meaning the total resistance will be, they are in series, so we'll add the two resistances to come up with 2R. Then P total will be V squared over R total to give you, which gives you that. So this is the power, this is the PD, and this is the R total. Therefore, I'll cross multiply this one this side to come up with 800 R equal to this, so this squared gives you that. Then make R the subject to give you 72 ohms. So that was Roman 1. Roman 2, the one, the power developed when the elements are connected in parallel to the same supply. So what if they were connected in parallel? It implies that total resistance would be product over sum. So total resistance will be product over sum, which is 36 ohm. Therefore, the power will be V squared over R. V squared is that, R is that, to give you 1600 watts. So power developed by either element is to 800 watts. Then question 7 came from UNEB 1990, paper 2, question 3C, and it says, figure 1 shows two cells, each of internal resistance 1 ohm, connected to a circuit which includes switch S. Switch S is there. Roman 1, what is the reading on the ammeter when switch S is closed? And Roman 2, what is the power developed in the 4 ohm resistor when switch S is closed? So they want the reading of this ammeter and also the power developed in the 4 ohm resistor. So these are two cells, they are in parallel, meaning the PD is the same. But the resistance is not the same. Resistance will be got by combining the two resistances in parallel. Okay, so we shall come here and say total internal resistance is by product over sum to give you 0.5 ohm. What about external resistance? External resistance will be got by first combining these ones in parallel, then you join them to this which is in series to give you 6 ohm. Therefore, E is equal to I in brackets R plus R, small r. Therefore, substitute E is that, I we don't know, external resistance we know it is 6, and small r we know it is 0.5. Therefore, make I the subject to give you that. Meaning that ammeter reading is that. Then for Roman 2, what is the power developed in the 4 ohm resistor when switch S is closed? Power developed in this 4 ohm. We know that the current flowing through the 4 ohm is the total current. So we shall come and say that power is equal to I squared R. And that gives you I here and R here to give you this as the power they wanted. So now we shall go to another part. So we have looked at electrical power, then we have also looked at the electrical energy, and now we are going to look at power rating of electrical appliances. So all electrical appliances are connected in parallel, so that each is at the same voltage. And also all electrical appliances are marked showing the power rating in watts and the voltage in volts. So all electrical appliances will always have these power ratings in watts and voltages in volts. The power of an appliance indicates the amount of electrical energy it supplies, or the amount of work it does per second. For example, the rating this 240 volt 60 watts on an electrical appliance means that that appliance supplies or consumes 60 joules of electrical energy every second when connected to a 240 volt mains supply. You can also define it in this way, that the rating of 240 volt 60 watts on an electrical appliance means that the appliance works on a PD of 240 volt and its output is 60 watts. Any of the two is okay. So that we shall go through these questions. Question 1 came from UNEB 1999, paper 1, question 6, and it says an electrical appliance is rated 240 volt 60 watts. Part A, what do you understand by this statement? So here you shall write and say that the rating this on an electrical appliance means that that appliance supplies or consumes 60 volt of electrical energy every second when connected to a 240 volt mains supply. Alternatively, you can say that this rating on an electrical appliance means that the appliance works on a PD of 240 volt and its output is 60 watt. So any of the two explanations is okay. That was part A. Part B says calculate the current flowing through and the resistance of the appliance when the appliance is operated at the rated values. So we got voltage and power. Now they want current and resistance. We shall say that first of all, power is equal to IV. So I can substitute for power and the voltage and be able to get the current. Okay, but they also ask for resistance. So come and say that power is V squared over R. So I substitute for power and voltage and make R the subject. So when I cross multiply, this goes this side to come up with this. Then this squared gives you that and make R the subject to come up with 960 ohms. And that's what they wanted. Then question 2 came from UNEB 2001 paper 1 question 48b, and it says an electric appliance is marked this. What does this statement mean? So we shall do the same. The rating this means that that appliance supplies or consumes 4 kilojoules of electrical energy every second when connected to a 240 volt mains supply. Alternatively, you can also say that the appliance works on a PD of this and its output is that. As simple as that. So any of the two is okay. Calculate the current drawn by the appliance in normal use. Power is equal to IV, so substitute for power for voltage to get the current, and that's what they wanted. Then question 3 came from UNEB 2017 paper 1 question 50c, and it says the filament of a lamp is rated 120 volt 30 watts. Calculate the resistance of the filament. So we know that P is equal to V squared over R. Come and substitute for P and for V. Then cross multiply, take this one this side to come up with 30R. This one squared gives you 14400. That means that when I make R the subject, I'll come up with 480 ohms. And that's what they wanted. Then question 4 came from UNEB 1994 paper 1 question 6b, and it says a bulb is rated 6 volt 12 watts. Calculate Roman 1 the current it takes. So we know power, we know voltage, so P is equal to IV. Substitute and make I the subject. Now that was Roman 1. Roman 2, calculate the energy it supplies in 30 seconds. So energy is power times time. Therefore, power is this and time is that. You come up with 360 joules. Then question 5 came from UNEB 2003 paper 2 question 6c, and it says a bulb is rated 12 volt 36 watts when used on a 12 volt supply. Roman 1, how much current does it draw from the supply? And Roman 2, what is its resistance? So we know power, we know voltage, so P is equal to IV, substitute for P and for V and make I the subject. That is Roman 1. Then for Roman 2 they want resistance, so V is equal to IR, substitute for V and for I, make R the subject, and that's what they wanted. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on commercial electrical energy. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that you can all benefit as a family.